My name is Moulick, Assistant Professor of Electrical Engineering Department of Haldia Institute of Technology. Today we are going to discuss about single phase full wave controlled converter, is full wave controlled rectifier, bridge connection with resistive load. Now for any power electronics converter, we need switches. So for single phase full wave controlled rectifier, obviously we need switch, and the switch that we are going to use is thyristor. So this is the symbol of thyristor. Now as you can see, there are three terminals: anode, cathode and gate. Now how this switch is operated? Whenever anode is more positive than cathode, thyristor gets forward biased. Now unlike diode, thyristor does not turn on whenever it is forward biased. To turn on thyristor, we need to provide gate signal at this gate terminal. So to turn on thyristor at forward bias condition, we need to apply the gate signal. And how to turn off thyristor? The turn off of the thyristor is not in our control. Thyristor is turned off whenever it is reverse biased. What is the meaning of reverse biased? That is, the cathode is more positive than the anode. Whenever thyristor, in case of thyristor, cathode is more positive than anode, it is reverse biased and automatically it is off. So thyristor is a semi-controlled switch where turn on is in our hand. Whenever it is forward biased, by providing gate signal, we can turn it on, but turn off is not in our hand. Whenever thyristor is reverse biased, it is turned off. Now we are going to go to the single phase full wave controlled converter circuit. So I am going to draw the circuit of single phase full wave controlled converter. So this is the circuit diagram of single phase full wave controlled rectifier. So in this bridge connection, we use 4 thyristors: T1, T2, T3 and T4. Why the naming is like this? That is, this is T1, T2 and this is T3, T4, that we are going to discuss. Single phase sinusoidal supply voltage Vs is connected. As I said, we are going to discuss it for resistive load, R load. Example of R load like bulbs are the examples of R load. So V0 is the output voltage. The polarity that we have considered is plus in this side and minus in this side. The current direction I0, this polarity we have selected. Now step by step we are going to draw the waveform for supply voltage, output voltage and output current. First, the sinusoidal supply voltage. So this is the omega t axis. This is the supply voltage Vs. So obviously it is a sinusoidal supply voltage. So it will look like this. I am going to draw a single cycle. So this is the supply voltage. I am drawing two blank profiles. One is for output voltage V0, another is for the output current I0. This is 2 our pi, this is 0, pi and 2 pi points. Now, in the positive half cycle, say this is positive and this is negative. So this will come here plus and here minus. Now at this condition, what we can see is that plus is connected to anode of thyristor T1. That means anode is more positive than the cathode. So in this condition, thyristor T1 is forward biased. On the other hand, in this leg, plus is connected with the cathode of thyristor T4. So that means in this leg, T4 is reverse biased. So T1 is forward biased, T4 is reverse biased. What about this leg? Negative is connected with the anode of thyristor T3. So that means T3 is reverse biased, whereas negative is connected with the cathode of thyristor T2. That means thyristor T2 is forward biased. So in the positive half cycle, if this is plus and minus we consider, then T1 and T2 are forward biased, T3 and T4 are reverse biased. But as I said, whenever thyristor is forward biased, it is not turned on. At forward biased condition, if we give gate supply, then only it is turned on. So that means, say at some point we have to give the gate supply to make it on. Say near around, I am using a different color. Say at this point, I am providing the firing angle. And so at this point, we are providing the firing angle. So when this angle is called the firing angle and it is denoted by alpha. So at alpha firing angle, we are going to trigger thyristor T1 and T2. Whenever thyristor T1 and T2 is triggered, that means it is turned on. And when thyristor T1 and T2 is turned on, at that time current will start to flow. What will be the direction? I am showing you the direction from supply, then thyristor T1, then through like this, then resistive load, then thyristor T2 and back to the negative. So this will be the path of current. Supply, thyristor T1, resistive load, T2 and back. So that means from alpha point onwards, whatever the supply voltage, through this T1 and T2, it will appear across the output, that is V0. Before alpha, all the 4 thyristors are off. So before alpha, output voltage is 0. After that, whatever is the supply voltage through T1 and T2, it will appear across the load. So it will look, so from this point, this voltage will appear across the output. Up to which point? Up to point pi, because, so this is pi, up to pi. Why up to pi? Because after pi, just a minute, I am just remove the, so it will look like this. So after this is the point pi. After pi, what will happen? After pi, negative half cycle will begin, and in the negative half cycle, the potential of the supply will get reversed. That means so after pi, this will become minus and this will become plus. So if after pi this is minus and plus, automatically thyristor T1 and T2 will get reverse biased, and as I said, turn off of the thyristor is not in our control. Whenever it will get reverse biased, it will turn off. So that means from alpha to pi, the supply voltage through thyristor T1 and T2 will appear across the load. So this supply voltage will appear across the load. And whenever pi reaches, negative half cycle begins. So polarity will become this, T1 and T2 is reverse biased and these thyristors are off. So what will be the current from this alpha to pi duration? There is a resistive load is considered. So the current waveform will be similar to the voltage waveform, just one difference. The peak of the output voltage will be same as the peak of the supply voltage. That is, at 90 degree, it will be Vm. The peak is Vm. So here also, if it gets the 90 degrees, say I am taking this one as 90 degree. So here also the peak will be Vm because the supply voltage appears in this time at the output. So peak is same. Here for current, peak will be voltage, peak voltage divided by resistance. So here peak will be Vm divided by R. Okay. Now let us go to the negative half cycle. What happens in the negative half cycle? Negative half cycle, we have already discussed. The polarity will become this. This is plus, this is minus. T1 and T2 is reverse biased, and T3 and T4 are forward biased. Whenever T3 and T4 are forward biased, it will be not turned on till the time we will give the firing angle. So let us assume that at the same point where we have fired thyristor T1 and T2, similarly at pi plus alpha, at this point, at pi plus alpha, this angle is pi plus alpha. At alpha we have triggered T1 and T2. T1 and T2 conducted for alpha to pi. After pi, T1 and T2 is reverse biased. T3 and T4 is forward biased. So after pi, alpha period, that is total pi plus alpha, at this point we are going to trigger T3 and T4. When T3 and T4 is triggered, I am showing you what will be the direction of current. So again, from supply, from positive supply, T3, then load, then T4, then back to negative. Again, from supply positive, then T3, then load, then T4 and back to negative. In this way, the current will flow. So as you can see, though the supply has reverse, but this supply in rectified form, that means this will be same, here will be positive, here will be negative. Same in the rectified form will appear across the load. So that means here from pi plus alpha to 2 pi, the supply voltage in a rectified form, it will get rectified. Plus will become here and minus will come here, as was like in positive half cycle. So this supply voltage in a rectified form will appear across the load like this. So this is pi plus alpha to 2 pi, will get this supply voltage in a rectified form here. So here also, if the peak voltage is Vm, similarly this is voltage. So peak voltage is Vm. Here also you will get Vm, and this current is Vm by R. So supply voltage in a rectified form will appear across the output. This will be Vm, and this current will be Vm by R. So in this way, for each of the positive and negative half cycle, we will get the output voltage in a rectified form. That is, output voltage is always positive. Output current here also is always positive. This kind of waveform we will get for single phase full wave controlled converter. Now why it is called controlled? Because here the output voltage or the current we can control. How we can control? For that we need to derive the equation of the output voltage. For that I have to remove the circuit diagram. I am removing the circuit diagram so that looking at the waveform we can derive the output voltage. So I am removing the circuit diagram. So if we want to derive the output voltage, as we can see, after pi, the waveform is repeating itself. We are going to derive the average output voltage V0. So here from the waveform of V0, what we can see that after pi, the waveform is repeating itself. So the period is pi. So 1 by pi, in this total pi period, what will happen? From alpha to pi, the waveform is similar to the supply voltage, it is 0. From here also we can see from pi to pi plus alpha, the voltage is 0. From pi plus alpha to 2 pi, the supply voltage obviously in a rectified form but following the same equation is in the output voltage. So total period is pi, after which the waveform is repeating itself. Total period is pi, and in this pi period 0 to alpha it is 0 and alpha to pi, from alpha to pi the output voltage is following the supply voltage waveform. So that means I am not writing 0 to alpha portion. From alpha to pi, the waveform output voltage is same as the supply voltage. So Vm sin omega t d omega t. This will be the average value of the output voltage. Why I have not considered 0 to alpha? Because at this point the output voltage is 0. So now let us derive it. 1 by pi, take Vm outside, integration of sin omega t, that is minus cos omega t. The limit is from alpha to pi. So that means it is coming as Vm by pi minus cos pi minus of cos alpha. So minus cos pi is minus cos pi is 1. Cos pi is minus 1. Minus of minus 1 is 1. Minus plus cos alpha. So as we can see, output voltage V0 is Vm by pi 1 plus cos alpha. So that means if we vary this firing angle alpha, the output voltage can be controlled. So that's why it can be said this is a controlled converter or controlled rectifier, because by controlling the firing angle alpha, we can control the output of the rectifier. What will be the average current I0? There is R load, so I0 will be V0 by R. One more thing, as we can see in a single supply cycle, I have drawn one cycle of supply voltage. How many ripples of output voltage we are getting? 1, 2 ripples. Output voltage is positive, but it is not a constant DC. We are getting 2 ripples. So from that we can find out what is the ripple frequency of single phase full wave rectifier. Rectifier converts we know from AC to DC, but the DC, if we do not use any filter, the DC will not be pure DC. There will be some ripples. What will be the ripple frequency? So the ripple frequency is, we have to find out that for a single cycle how many ripples are there. Here for a single supply cycle there are 2 ripples. So that means if the supply frequency is f, the ripple frequency will be 2 into f, because there are 2 ripples in a single supply cycle. So ripple frequency is 2f if the supply frequency is f. Suppose if the supply frequency is 50 Hz, then the ripple frequency will be 100 Hz. So this is single phase full wave controlled rectifier with resistive load. We have derived the average output voltage, average current, and the different waveforms for the single phase full wave controlled rectifier with resistive load. Thank you.